Okay. Thank you for introduction. My name is Yongzhou Chen, and today I'm going to present our project, Channel-Aware 5G RAN Slicing with Customizable Schedulers. This is a joint work with Ruihao, Haitham, and Radhika Mittal. Network slicing is the key feature introduced in 5G standards. With network slicing, the network operator divides resources which includes core resources and the radio resources among different group of users called slices or enterprises. Here, a slice can be a mobile virtual network operator such as Google Fi, Mint Mobile, or specific applications such as a team of drones doing citywide sensing. Each slice then can customize its virtual network by dividing its allocated resources across its own users. This allows the network operator to isolate resources across slices based on their demands and allow the enterprise to tailor their virtual network as per requirements. Our work focuses on RAN slicing, that is the slicing of radio resources. The allocation of radio resources to a user determines the link capacity from the base station, or GNOB. Downlink radio resources are divided in both frequency and time domain. And the smallest unit of allocation is called a resource block. A resource block spans a fixed transmission time interval, referred as TTI in the time domain. In the rest of my talk, I'll use the term RB for resource block. With 5G RAN slicing, the network operator runs the inter-slice scheduler, which divides RBs across slices. Then, each slice runs the intra-slice scheduler to divide its allocated RBs across its own users. We refer those intra-slice schedulers as enterprise schedulers. Every enterprise scheduler can customize its scheduling policy. For example, a slice may want proportional fairness across its users. Another slice may want to maximize the throughput. Or another slice may want to prioritize some users over others, and so on. A RAN slicing system should meet three key objectives. The inter-slice scheduler should enforce weighted fairness across slices. The slicing system should support customizable and diverse enterprise schedulers. It should also achieve high spectrum efficiency, that is, high throughput. We argue that a RAN slicing system needs to be channel-aware to meet those requirements. Let me first explain the need for channel awareness. When we are dividing RB across users, not only the number of RBs allocated to a user matters, which RBs are assigned is also important. This graph drawn from real-world traces with channel quality across all RBs of a user for a given TTI. The x-axis is RB ID, and the y-axis is the link capacity of the RB if it's allocated to that user. As you can see, different RBs have significantly different channel quality. For example, if the RB is allocated 31st RB, it will achieve the data rate of 500 KB per second. But if it's allocated the 75th RB, it will only get 20 KB per second. Now, the red line shows the channel quality distribution for the second user. For a given RB, different users have significantly different channel quality as well. This phenomenon is well known as frequency selective fading. Therefore, channel-aware RBs allocation is important in 5G scheduling. However, existing RAN virtualization techniques are not entirely channel-aware. The inter-slice scheduler divides RBs across slices, agnostic of channel quality. Each slice can allocate its RBs to users in a channel-aware manner, though. In the first example, NVS allocates RBs to slices in time domain, which means all RBs in the TTI go to one slice. The enterprise scheduler can be channel-aware. For example, it can maximize the throughput by allocating assigned RB to the user that achieves the highest data rate. Or it can have a proportional fair policy that augments the maximum throughput by incorporating fairness across users. In the second example, Flare static assign a dedicated chunk of spectrum to a slice. The advantage of those approaches is that it cleanly decouples the inter-slice and the enterprise scheduling. But the problem is that the inter-slice scheduler is channel agnostic. So why is channel agnostic inter-slice scheduler a problem? We'll use this example to highlight that. Here, we divide 4 RBs to 2 slices with same weights. Every slice allocates the same amount of RBs to its users. These numbers represent the data rate every user can achieve for each resource block. If we divide RB to slices in the time domain, all RBs of a TTI goes to 1 slice. In the first TTI, the sum data rate after calculation is 40 KB per second. In the second TTI, the rate is the same, 40 KB per second. If we divide RBs to slices statically, which can also be suboptimal, notice that the allocation results in 2 TTI are the same. So here, the average data rate is 20 KB per second. Even if the enterprise scheduler is channel aware, if a slice is assigned a bad set of RBs to begin with, it cannot squeeze out more throughput. However, if we look into the channel quality distribution, we can find that users in slice B have higher quality in the first 2 RB, while users in slice A have higher qualities in the last 2. Therefore, the channel-aware allocation can achieve higher data rate, which is 60 KB per second. We argue that channel awareness is needed at both levels. The channel-aware enterprise scheduler can ensure that each slice can squeeze out high spectrum efficiency from the allocated RBs. However, channel-aware inter-slice scheduler can ensure that each slice gets a good set of RBs to begin with. While the former is allowed by existing RAM virtualization techniques, the latter is not. However, enabling channel awareness at both levels is difficult. The challenge is due to the cyclic dependency between the inter-slice scheduler and the enterprise scheduler. In order to determine the channel quality associated with every RB for every slice, the inter-slice scheduler needs to know which user will be scheduled at each RB, and this is determined by the enterprise scheduler. To make its scheduling decision, the enterprise scheduler needs to know which RBs are allocated to it, and this is determined by the inter-slice scheduler. We'll use another example to highlight the problem stemming from this cyclic dependency. Here, the network operator allocated 2 RBs to slice B, and the enterprise scheduling policy assigned RB to the users with highest channel quality under the constraint that each user gets at the most 1 RB. If the slice is given RB1 and RB2, RB1 is assigned to the user 3 since it has the highest channel quality, and user 3 already been assigned 1 RB, the RB2 goes to the user 2 in this case. If the slice B is given RB2 and RB3, then RB2 is assigned to the third user, in the third unit in this case. For the same resource block, RB2, it's assigned to different users with different channel quality in 2 scenarios. Therefore, the inter-slice scheduler cannot determine the channel quality of RB2 associated with slice B. How do we work around this cyclic dependency? Our approach is based on a simple insight. If the inter-slice scheduler can issue a query to each enterprise scheduler, if I give resource R to slice S, which user in slice A will get the resource R? If the enterprise scheduler can answer this query, we can break the deadlock. However, being able to answer this query restricts the enterprise scheduler to allocate RBs to users independent of future given RBs. Thus, it must be greedy. However, we found many existing standard scheduling policies are already greedy. The inter-slice scheduler should also be greedy to allow the enterprise scheduler to account for historical allocations and user demands. Based on this insight, we built our system, Radio-Saber, the first RAM slicing mechanism to support channel awareness at both inter-slice and enterprise scheduling. I'll talk about 2 key components of Radio-Saber: channel-aware inter-slice scheduler and a framework for customizable enterprise scheduler. Let me start with the channel-aware inter-slice scheduler design. In this example, we allocate 3 RBs to 3 slices with same weights, and there are 6 users in total. Firstly, RadioSaber computes RB's quota in each TTI for each slice based on their weights. The details how we compute the RB quota are listed in the paper. Then, RadioSaber picks a RB for allocation. Let's say the example is first RB. RadioSaber issues a query to every enterprise scheduler asking which user in the slice will get the RB if the RB goes to that slice. The enterprise scheduler runs as a subroutine and can answer this query since it's greedy. Lastly, we assign to the slice which achieved the maximum channel quality for it and hasn't satisfied the slice RB quota. We'll do the similar procedure for the second RB and the third RB. Picking the order in which resource blocks gets assigned is also important. Please check those details in our paper as well. I now move to describe how RadioSaber can support customizable and diverse enterprise schedulers while restricting them to be greedy. As we mentioned before, the enterprise scheduler policies should consider many factors, such as channel quality, the fairness between users, the flow priority, and the queuing delay. We want to allow slices to customize their scheduling policies based on those factors as comprehensively as possible. So we designed 2 paradigms. In the first paradigm, the slice will pick a user first and schedule the highest priority flow for that user. The slice can set parameters to tune the relative weightage of channel quality and historical allocation when selecting a user. And this is inspired from the generalized proportional fair scheduler. In the second paradigm, we'll first pick the highest priority level first and pick the specific flow in that priority level. The slice can set the parameters to tune the relative weightage of channel quality, historical allocation, and the headed packet delay when selecting a flow. And this is inspired from another work. We extend Open5GS to support RadioSaber control workflow, which allows slices to configure their scheduling policies in the 5G core. RadioSaber will propagate the parameters from the core to base station for scheduling. We implemented the scheduling algorithm RadioSaber in an open source RAN simulator. We extend the simulator to 5G configuration and use trace-driven simulation using collected channel quality traces from LT scope. Our simulation supports as many as 800 users. We use the simulator to extensively evaluate the performance of RadioSaber, and in this talk, I'll show 2 key results. RadioSaber can correctly enforce isolation and weighted fairness across slices, and the RadioSaber achieves higher overall throughput than state-of-the-art inter-slice scheduler. Our evaluation configuration comprised 20 slices, each with 5 to 15 random users. The first 10 slices have a weightage of 1 and apply maximum throughput enterprise scheduler. The last 10 slices have weightage of 3 and apply proportional fair enterprise scheduling. Our baseline NVS, state-of-the-art inter-slice scheduler, and no slicing, a global proportional fair scheduler across individual users. In this graph, the x-axis is the slice ID, while the y-axis is RB allocated to every slice per second. We can see both RadioSaber and NVS allocate 3 times more RBs to the last 10 slices compared with the first 10, which enforce weighted fairness and isolation. No slicing cannot guarantee any isolation or fairness at all. The right graph shows the aggregate throughput in every slice. We can see RadioSaber achieve higher throughput compared with NVS in almost every slice due to its channel-aware allocation. We also evaluate other aspects of Radio-Saber. Radio-Saber supports diverse and customizable enterprise scheduling policies. Our performance benefits hold as we change the number of slices or users per slice. Radio-Saber has low runtime overhead, and the scheduling latency is within a TTI. And more results in our paper as well. To summarize our work, we identified a fundamental challenge in the channel-aware RAN slicing, which is due to the cyclic dependency between the inter-site scheduler and enterprise scheduler. And we break this cyclic dependency by restricting both to be greedy. We built Radio-Saber, the first RAN slicing system that's channel-aware at both levels and provides parameterized interfaces to customize the scheduling policy. Our system achieves 17 to 72% higher link capacity compared with state-of-the-art. Our website and code are available online, and thank you for listening. I'm ready for questions.